Hi everyone, in this video we are going to discuss connecting our concept of delta G naught to equilibrium. So up until this point we've had a couple of different interpretations of delta G naught. We've used it to discuss favorability, right? Where we've said that a negative delta G was thermodynamically favorable, and we've said that a positive delta G was thermodynamically unfavorable. We have also looked at it in terms of work. So where we think of a negative delta G as work out, coming out of the system being done on the surroundings. So we have labeled that exergonic. And we've also thought about delta G greater than 0. That's a G. Delta G greater than 0 as work having to come into the system to make it happen, and we've labeled that endergonic. So now we're going to look at a third interpretation of the delta G naught value and connect it back to equilibrium. All right, so how are we going to do that? Well, the best way to do that is to look at a diagram of a reaction. So let's take a kind of generic acid dissociating. So we'll call it HA. And A could be acetate, it could be nitrite, any weak acid, all right? And we're going to think about two very different situations for this acid. So one possibility would be that the acid could exist in such a way that at equilibrium, it is mostly dissociated, all right? So we could have a situation where most of the acid is dissociated, and maybe one out of every 5 or 6 of these is still together as the associated HA, but mostly we have H plus ions, and we have A minus ions free floating in solution, okay? So this would be a case where you have mostly products. And going back to our interpretation of the equilibrium constant, remember that K is products over reactants. So if we have mostly products, a large number over a small number, right? That means that if this number is big and the number down here is small, this value is going to be greater than 1, so a K greater than 1. What we're going to find is that the delta G naught for this reaction, when we calculate it, that delta G naught is going to be less than 1. So in our previous discussion, we've talked about how, delta G less than 0. A delta G less than 0, a negative delta G, we would have called that thermodynamically unfavorable previously. And now we're going to think of it additionally as, well, for a reaction that reaches equilibrium, that it is a negative delta G is going to correspond to mostly products being present, but still maybe a few reactants depending on exactly what that delta G number is. On the other hand, we could imagine that our imaginary weak acid mostly remains associated, and maybe 1 out of every 5 or 6 are dissociated. So in this case, we have a situation where at equilibrium, and again, these are both at equilibrium. Okay, I want to emphasize that these are both at equilibrium. That if you had a case where it was mostly reactants, that the K, which is again products over reactants, the K value this time would be less than 1, right? Because we would have a large number in the denominator, a small number in the numerator. And this would correspond, when we do the calculation, to a delta G naught greater than 0. Again, we would have said before this was unfavorable. And by unfavorable, we mean the reaction doesn't go forward. It mostly stays in the reactant form, all right? And that's what we see here. So we're just taking our previous understanding of delta G naught and our understanding of equilibrium, and we're kind of combining them in such a way that they're going to be able to complement each other. We'll take this another step tomorrow, but for now we're going to also introduce an equation that relates these. It turns out that that there is a simple equation to relate these, that delta G is equal to the negative times RT times the natural log of the equilibrium constant. So R here is our old friend, the gas law constant, although it's in a slightly different unit than what we would normally have used it in first semester. It's 8.31 joules per mole Kelvin. The temperature, as always, is temperature in Kelvin. And of course, the K here is our equilibrium constant. Ln is our old friend, the natural log function, all right? So anytime that you have one of these values, you're actually able to calculate over to the other. What you'll find is that this natural log function, if the K is greater than 1, this ln will be positive, and the delta G naught will come out negative because of the negative sign out in front. If instead you plug a K value that's less than 1, the ln of a value less than 1 is negative. Two negatives is going to give a positive delta G. And so that's the negative sign here out in front is what's going to make these two agree with each other, so that a K greater than 1 will correspond to a negative delta G, a K less than 1 will correspond to a positive delta G. All right? So all we're doing here is we're taking another interpretation of delta G naught. We've seen that there's more than one interpretation, and we're merging it with our understanding of equilibrium. A reaction that at equilibrium is mostly products. Before we would have just said it has a K greater than 1, and now we're going to add that that's a delta G naught less than 0. In other words, a negative delta G. If at equilibrium we find that a reaction exists mostly as reactants, we would have said before that's a K less than 1, and now we're going to add on top of that that's a positive delta G naught.